Today we are going to study about density of states of a three-dimensional material. So here we are considering a cube with length L. So we're going to find out that how many number of states will be present in this cube. Density of states actually means that the number of states per unit energy per unit volume. So density of states would mean that number of states per unit energy per unit volume. So this is what we are going to calculate. How many states are allowed? So just understanding first what is the meaning of states first of all. So if we take this lattice and let us say we are just considering one layer of atoms in this cube of length L. So in this length we see that because the quantum particle that we're talking about here is the electron, and it will behave like a wave, and because the length of this length and width and height of this material is has some finite value, therefore it will have some finite number of modes that will be possible for that electron. So those modes will actually can exist in this manner. So in this length L, the maximum wavelength possible will be lambda upon 2. So and the next possible mode will be lambda, and then 3 lambda upon 2, and so on. So it means that in this length L, the number of modes that are possible will be n lambda upon 2. So from here we can find that k will turn out to be n pi upon L. So it means k will get quantized. It means the wavelengths possible, they are quantized. Only fixed number of wavelengths will be possible. So that means that if lambda is fixed, it means k is also fixed. So it means that the wave vectors associated with this wavelength will also be fixed. So if these wavelengths are possible, then it is also possible that there will be some maximum wavelength and there will be some minimum wavelength that will be present in the lattice. So the minimum k value will be for the maximum wavelength, and the maximum k will be for the minimum wavelength, which will be the interatomic distance between the two particles. So if we know the minimum k and maximum k, we can find the number of states that will be permitted. So it will be the maximum k upon minimum k. Also in the k space, you see that k values will be are given by n pi upon L. It means that the first k value will be pi upon L, second will be 2 pi upon L, 3 pi upon L, and so on. So it means that the distance between two k values will be pi upon L. So if this is the k space, let us say that this is x axis and this is y axis. So let us say this is ky and this is kz or kx, or this is ky and this is kx. Then it means the distance between, so these are all k values, k points that are allowed. So in the this is for the real space, and this is in the reciprocal space, in k space, momentum space. So the distance between two k points will be pi upon L. But that also means that one point occupies pi upon L distance. So it means that if one point, so if it is two-dimensional lattice, but if it is a three-dimensional lattice, like I've drawn here the cube, so if it is a three-dimensional lattice, then it means that the volume occupied by one lattice point will be given by pi upon L cube. So that is why we have written here pi upon L cube. Now in a three-dimensional material, the k space will look something like this. And let us also explain it by taking an EK diagram of a bulk material, three-dimensional material. So you see that for each value of k, there will be a energy value that will be present. So it means that if we know the number of k values that are present, we can find out the number of energy states that are permitted. So it is fair enough to count the number of k values in space. So that is why we are usually talking about the k vectors when we are talking about the density of states. So for such a three-dimensional material, we have the EK diagram looks like this, and the dispersion relation is given by h bar square k square upon 2m, and because it is a equation of parabola, and that is why it is a parabola here. So from here we can find out the value of k from here. Okay. So and also what else does it mean? It means that k actually is composed of three components, kx, ky and kz. So we can write it as kx square, ky square and kz square. So it means that this actually is an equation of sphere. You can also use this equation also. That will also not change anything. It will just change the radius. So here it is E minus EC. The radius k, we'll find out the value of k from here. The radius will be 2m into E minus EC upon h bar squared under root. That will give you the radius of a sphere that is drawn in kx, ky, kz space, while here it is just e 2m star e upon h bar square. So that is the only difference. So so it is a sphere, and the maximum value of k can be got by taking the magnitude of this and finding out what is the maximum energy that is, and that is possible in that particular lattice or that particular material. So it means that in this sphere, which so it will look something like this. So it means that if we know the volume of this sphere and we know the volume of one state, we can find out the number of states that are possible, the number of modes that are possible, the energy states that are possible. So in order to do that, the volume of this sphere in k space will be 4 upon 3 pi k cube, and then we'll have to divide it with 8 because we are only concerned about the positive k axis, and therefore in this sphere only the positive part of the sphere will we will be using on the positive part of the sphere, because only positive k values make some sense. So that is why a factor of 1 upon 8 is there. Also a factor of 2 is required because each state can actually have two spin states. So then, and also divided by the volume of one state, which is pi upon L cube. So 2 cancels with 8, we get 4, 4 cancels with 4, and so on. And so from there we get number of states to be k cube L cube upon 3 pi squared. Now we can change it in terms of energy. So you can use this equation and find out the value of k. Put this value of k into this equation, and you can get this relation. And from here, because density of state is number of states per unit energy per unit volume in the real space. So it will give you 1 upon L cube of derivative of n with respect to E. So when you take a derivative of n with respect to E, you get this equation. So this will give you the density of states in three-dimensional material. So it means that in a three-dimensional material, it depends upon E minus EC under root. So if we plot it, it turns out to be something like this. So because EC is a constant and E we are increasing gradually. So initially the difference will be very less, and then it will keep on increasing. But ultimately, because EC is a constant, so when E becomes very large, then it will be almost constant. So that is why this graph actually, it is initially less, it increases and then it saturates. So this is how the density of states will look like for a three-dimensional material.